Hey everyone, let's talk about digit DP today. So, although it might sound like a pretty complex idea, but it's actually quite comprehensible. Basically, what we do is instead of handling it as a number, for example, it is a number, we don't treat it as a number, but we treat it like a string. So, consisting of 0 to 9 string. So for example, if the current digit is 7, then the next digit can be 0, or it can be 1, or it can be 2, or it can be all the way to 9. And after having the first layer, and if we go from 0 here, it can also be 0 again, and it can be 1, it can be 2, and it can be all the way to 9. And similarly for 2, it can be 0, it can be 1, or it can be 2, all the way to 9, etc., etc. So basically, if we do this tree will iterate all the possible numbers that we can find. So at this point, you may wonder, why not just consider the number as a numeric value instead of doing this kind of recursion stuff? Simply put, if there is only a 10-digit number, it seems very small, right? It's just only a 10-digit number, but will be something like 10 billion, which exceeds the processing capabilities of many programming languages. Moreover, most integer size of the programming language just ends with about 2 times 10 to the power of 9. It might not even be possible to treat the input as a number if there are like 10 or 15 digits following by it. However, if we treat it like a string with a size of 10, then we can do pretty much any operation on it. Because 10 is such a small number, we can do n squared, where n is the size of 10, or n cubed, or even n to the power of 4 would be okay. That's why the limit becomes so much more linear when we think of the input as a string compared to think of the input as an actual number. Moreover, sometimes using recursion might help us to eliminate the repeated calculation. Let's take a look at this example problem. We need to count total where every adjacent digit must have an absolute difference of exactly 1. So remember, previously we said we can recurse to 0, 1, all the way to 9, correct? But if we do recursion, now we don't have to consider this. We just need to consider 6 or 8, because these are the two that have the exactly difference of 1 comparing to 7. So we don't have to consider 5, we don't have to consider 4, we don't have to consider anything else. And also you can see the number, like I mentioned, the number sometimes might be as large as 10 to the power of 100. So it means that this is about 1 trillion sized, which is not even possible for us to treat it as a number in many programming languages. So which also hints us that digit DP might be necessary. Then by recursing 6 and 8 and calculate the result respectively, we can also do some sort of caching, so we don't have to repeatedly calculate the same thing, which is also where the digit DP, where the DP part comes into play. Let's say we calculate this thing, 6, we know the result of 6, and later on, we have to consider 5. We know 6 is also having the absolute difference of 1 comparing to 5. So it will visit this as well. But now, since we already calculate and store the result here, we don't have to redo this whole thing, which is how we can achieve a more efficient solution. So then that's basically all the intuition of this problem. Let's see how can we implement it in details in code. So first, I'm just going to use some helper method to help me calculate the answer under the mob. Basically, it just makes it never exceed the number of mod, because the number could be very big. Then I will define a helper method here, which will just return forced when the input number is not actually a stepping number. The implementation is simple. I'm just going to iterate every position of the number, then I'm just going to compare with the previous one, and if it is not equal to 1, it means that it is not actually a stepping number, and otherwise we just return true at the end to indicate that it is a stepping number. Then I'm going to define a helper method first. This helper method will get the answer that are smaller or equals to none. So you can imagine now I'm only care about the higher bound. I don't care about the lower bound at the moment. Then I'll have the LRU catch to do the DP part for me. Then I will create this recursive call, which the first index will be current index, which means the current index of our number that are trying to build is tight, indicates whether we should stay within the non-current index. So if it is tight, then we should go under this non-current index. And if it is not tight, then we can go above it, basically. The previous just means the previous digit that we have chosen. Exceeded means that, well, if we are meeting in a tight recursion, we can go exceed the digit, but after we exceed the digit, we don't want it to go above the higher bound. So we have some exceeded boolean to tell us that if there is some digit that has exceeded the previous digit or not. For example, this 1, 2, 3 is the higher bound. In here, we can do 1, and we can do 4 as well. But after we do 4, we cannot do any digit, even 0, because this 1, 4, 0 will be larger than 1, 2, 3. But we can end here. This 14 is also acceptable. That's why if we exceeded something in here, then we cannot reach the end of the length of the higher bound. That's why we will return 0 here if we exceeded something and reached to the end of the higher bound. Then we can initialize the answer as 1. Notice not 0 because we also choose to end the particular number at this point, which is also a valid option for us. This current digit is just the numeric value of the character that on the current index of num. Then, as I mentioned, we only have 2 options for each recursion call based on the previous. Namely, previous -1 or previous +1, because these 2 are the only thing that will have the difference equals 1 to previous. There are no other options. There's only 2 of them at most. But we also have to handle a case when it is previously 9, and 9 plus 1 will become 10. But 10 is not a valid digit. And also, if previous is 0, we can -1. and it will become -1. -1 is not a valid digit as well. That's why on line 16, we are handling that here. We will just continue when we meet these two numbers. Then, as I mentioned briefly, if the previous is a tight recursion, and then we have this choice greater than current digit, it doesn't mean that we cannot choose this current digit. It just means that if we choose this current digit, we cannot reach till the end. If we reach till the end, we just have this 0 in order to prevent it to be greater than the higher bound, basically. That's why if it is exceeded something, then we have to put true in the exceeded flag. But since we are having one less digit of our higher bound, so this thing will never be tight anymore. So we put false in here. That's one possible branching. The second branching is that when it doesn't exceed anything, then we will just continue the is tight. If it is tight and the current is also equals to the current digit, then it's keep being tight again. For example, we have a higher bound like 1, 2, 3 again. If we choose 1 here, then it's tight because this will mean that we can only choose up to 0 to 2 here. But if we choose 1 and then we choose 2 here, then it will keep being tight because on the next digit, it can only choose from 0 to 3 here. But if we pick 1 here, then for the next value, we can basically choose from 0 to 9. Because this 0 to 9 will be always less than the higher bound. That's why I'm saying that if it is tight, then we choose the number that is exactly the same as the boundary again, then it keep being tight. Otherwise, if we choose anything less than the number, then it will just stop being tight altogether. And we can choose whatever we want as long as it is fulfilling the absolute difference equals 1 requirement. And finally, we just return the result because we have considered all of these two possibilities. As I mentioned multiple times, there's only 2 possible scenarios. One is -1 and the other one is +1. All other digits will have a difference greater than 1 or not equals to 1. Exactly. So after doing all of this stuff, we can iterate every starting point of the first number. Basically, we want to start at the second number. This putting 1 in here, it stands for the second of the index because we start at 0 indexed for the num. Then we just brute force every possible start for our recursion. The start can go from 1 all the way to 9. We're using 10 here because in Python range, the second element is exclusive. So I write 10 here, and the last element will be 10 minus 1 basically. That's why this is representing 1 all the way to 9. And then we just have to return the answer. This answer stands for anything that is smaller or equals to none. And the answer that we are interested in is anything that is less than or equals to high minus anything that is less than or equals to low. Because anything less than or equals to high will automatically include everything that is less than or equals to low. But there is one catch here. If this particular low is the stepping number, then we have to plus 1 again. Because we have to consider them also. That's why we are doing this one if the stepping number is low. Otherwise, we just add 0. It just doesn't do the add basically. And that's basically the whole code. Let's try to run this. Okay, accepted. And I hope this was helpful, and I will see you next time. Bye bye.